Okay, so we know that for a graph to be differentiable, it has to be continuous. But there are two cases where a graph is continuous, but it's not differentiable. And I'm going to show you those right now and why this is the case. So the first one is going to be when we have what's called a vertical tangent line on the graph. So let's say this is our function, whatever, and then we have this really sharp vertical segment, and then it starts to curve off again, whatever the graph looks like on the other sides. This sharp vertical tangent, or vertical section, is what we call the vertical tangent line. So at this x value here, the derivative it's not going to be differentiable right there. And the reason for this is, so keep in mind, again, that the derivative is basically the slope of the graph. And so if this is a vertical line, what's the slope of a vertical line? We know that's undefined. So if the slope's undefined, the derivative is undefined, so we just say it's not differentiable right there. Okay, so the next spot where a graph might not be differentiable is going to be at the point of a sharp turn. So like right here, this graph is going down, immediately sharp turns to go back up. Unlike a parabola, where it's going to be going down and then curves into going back up very easily. Now the justification for why this isn't if it isn't differentiable is a bit more complicated, but the way we think of it is like taking the limit of the slope of the graph, basically. So if we take the limit from the slope on the left side of this graph, it's going to be all negative all the way down to whatever this point is right here. If we take it on the right side, this limit is going to be positive, positive, because it's basically going this way. This is negative, and this is positive. So because this is negative all the way up to this point, and this is positive all the way up to this point, the limit from the left does not equal the limit from the right. So that means the limit doesn't exist, and by that we're basically saying that this is not going to be differentiable. Unlike a parabola like this, yes, it's always going to be negative down here, but the negative starts getting smaller and smaller negative until it reaches 0 at this point. Just like here, how on the right side, it's getting more positive and positive basically, or whatever. It's approaching 0 at this one point. So here, it's not changing approaching 0, it's just that same negative or same positive. And over here, it's all curving into 0. So the fact that these kind of easily meet versus this graph not meeting at all really, and it's just sharp, that's kind of why. It's kind of hard to explain. We don't really need to know the justifications too much, but just know that a sharp turn and a vertical tangent line are where a graph would not be differentiable. So with that being said, I'm going to take you through 4 different example graphs, and we're going to try and list the intervals where the graph is differentiable, and then when it's not, we're going to say why it's not differentiable. So for this first one, we got this really nice curve, whatever. It looks really funky, whatever. Then, right here we got a vertical tangent line. So that's an important thing to note. A vertical tangent line at x equals 3. So at x equals 3, we know that's going to be a spot it's not differentiable. And then the slope just flattens out. Because it's flat, it's still differentiable there. The slope's just going to be 0, but that's still a slope, so it's still differentiable. So it looks like for our graph, if let's just say these are endpoints here, so we don't have to care about infinity or anything, it looks like for where it's differentiable, it's going to be from 0 with a square bracket because 0 is included, all the way until 3. And then it's not going to be differentiable at 3, so union. And then from 3 until 6. And so that is the interval. And why is it not differentiable at x equals 3? And that is because we have our vertical tangent line. And that's about it for this symbol graph. Okay, graph number 2. So it looks like this graph starts at -6, and it goes all the way until almost 0, until it just shoots up into the sky for infinity. And then if we look at it from the right side, it does that same exact thing. We start at 6, and we go backwards, it goes all the way up until 0, then it shoots up to infinity again. So it looks like it's differentiable everywhere, except for at 0. And the reason it's not at 0 is because of this time it shoots up into the air. And this is not one of those two special cases where it's not differentiable. This is actually because it's not continuous right here. We have a vertical asymptote. And if a graph's not continuous, then we know it's also not differentiable. So it's not going to be differentiable at x equals 0. So because of that, let's write our intervals now. We know that it's going to be from -6 to 0. It will be differentiable, but then also from 0 into 6. And then if we're going to say why it's not differentiable at x equals 0, then we say is because it's not continuous. And if we want to be more specific, we could write just at the end that we have vertical asymptote, or we could shorten that to just VA. Okay, we got our third graph here. It looks kind of like it's going to be it's a piecewise function or something. Got this kind of curvy graph until x equals 4, and then, sharp turn right here, so it's not going to be differentiable there, because sharp turn is one of our special non-differentiable cases. And then it just goes into a normal line. So it looks like just x equals 4 right here. It's the only spot it's not differentiable. So that we know, because of that, we know it's going to be differentiable from 0 to 4, and then union 4 to 7. And then if we're going to say why it's not differentiable at x equals 4, it's because we have a sharp turn. I cannot write properly, but yeah, sharp turn. I'm just bad at writing stuff. Yeah. And for this last one, this one looks the most complicated yet. So this one actually stretches out all the way to negative infinity. Then it's curving down here. And then this looks really vertical, so we got a vertical tangent line here. So this looks like x equals 2, so let's mark that. X equals 2 going to be a point where it's not differentiable. And it curves down, and we have a jump here. A jump means it's not continuous, so at this point it's also going to be not differentiable. So that's x equals negative 1. If we go back down to the bottom of the jump, it looks like it's just going straight up like a normal line. And then we've got another thing where it's not differentiable here. Got a sharp turn, immediately going from positive, jumps down to going straight negative. So it looks like it's going to be x equals 1, 2. Graph's drawn kind of bad there, but if we look, that's about x equals 3. So let's just say that's x equals 3, just for the sake of it. We know why, because there's the because there's a sharp turn. That's the point I was trying to get across, even if the graph's drawn badly, and that's about x equals 3. So if we write our interval excluding these values, remember these are going out to infinity this time, so our intervals are going to be negative infinity into negative 2. Negative 2 is part of this one, so we use square brackets, union. And then if we look at negative 1 does have a point, so we're going to use negative 1. Union again, and then goes to x equals negative 3. Or not negative 3, that's positive 3. So negative 1 to positive 3. So this is going to be our interval where it's going to be differentiable. And then if we have to give justifications for each of these 3 reasons that it's not. So the first one is going to be our vertical tangent. Our second one is going to be discontinuity because of a jump. And then our third right here is going to be a sharp turn. And that's about it. Okay, the next kind of thing we were shown in lesson 2.3 was where we're given a piecewise function like this, and we're given constants in here that we don't know the value of, in this case a and b. We want to solve for a and b, so f of x is always going to be differentiable across negative infinity to infinity. Now we've seen this kind of problem back in Unit 1, but we were trying to make it continuous the whole time. And when we did that, what we did was we took our 2 equations here, and we made them equal to each other. So in this case, it'd be ax cubed equals x squared plus b. And we're going to do that at the endpoint. So in this case, this would be true when x is equal to 2. And then if we did that, that means that if we solve for a and b there, then these 2 graphs would be connected at x equals 2, and it's going to be continuous. And so we're going to do the same exact thing here. The only difference is, let's say we were going to start doing this right now. So we're going to actually, we have our equation, and it says when x equals 2, so let's plug in x equals 2. 8 times 2 cubed equals 2 squared plus b. That's going to be 8a equals 4 plus b. Or if we want to move all variables to one side, 8a minus b equals 4. Now we're stuck. We only have we only have one equation. We don't have 2 equations to solve for both our variables. And this is where we have to think about that it's not only continuous, but we have to make sure the graph is differentiable. So to do that, not only do we have to make the function have these two equations equal, we're going to have to make its derivative have the equations equal. And to do that, what we have to do is we have to derive the piecewise function f of x, and then do the same process with that new piecewise function we came up with. So I'm going to erase this information here and just save our equation we made from this, or where we got our 8a minus b equals 4. So I'm going to save this so we can actually solve for a and b later. But now what we're going to do is we're going to take the derivative of f of x. So f prime of x is going to equal. So first we're going to take the derivative of ax cubed. And remember, a and b are going to be constants, and so we don't have to treat them like variables. So if, let's just say we're taking the derivative of x cubed, we would have 3x squared. But remember, a is a constant being multiplied to x cubed, so we're just going to have to multiply that into the derivative. So instead of 3x cubed, it will be 3ax cubed. And remember, this condition still applies, so this will happen if x is less than or equal to 2. Moving on to the next one, we have x squared plus b if x is greater than 2. And notice here that instead of being multiplied together, these two are actually added together. So we take the derivative of them separately. So if we take the derivative of x squared, we're going to get 2x. And if we take the derivative of b, remember b is a constant, so if we're just taking the derivative of b, we're just going to get 0. So 2x plus 0, so just 2x. And this will be if x is greater than 2. So now we could do that same process we did earlier. We're going to set these two equations equal, so 3ax squared equals 2x, and this will happen when x equals 2. Now if we plug in x equals 2 here, we will have 3a times 2 squared equals 2 times 2. In other words, this will be 12a equals 4, or a equals 1/3. And now, if you notice, we have a value for a equals 1/3. So we take this and plug this back into our original equation. So we have 8a minus b equals 4. Plug in a equals 1/3, we'll have 8 over 3 minus b equals 4. And let's write 4 in terms of over 3. That's going to be 4 over 1 is the same as 12 over 3. So now what we want to do is we're going to subtract 8/3 on both sides. So we'll get negative b equals 4 over 3, or b equals negative 4 over 3. And that is our values for a and b. And if you wanted to check that, you could just plug in a and b into f of x and into f prime x. And then if you did that, these should be equal when x equals 2, and these should be equal when x equals 2. Okay, the next thing we worked with is we are given 4 graphs of f of x. Like this would be like 4 kinds of, or we were given 4 graphs of functions basically, and then we were given 4 graphs of derivatives, and we had to match the function with the derivative. So please keep in mind before I go over this that this is all hand-drawn sketch, so it's not going to be perfect, but I hope I will try and be able to get the message across to you. So let's jump right into it. So these are the functions and these are the derivatives. And the first thing I notice is in number 4 for the derivatives, this looks like we have like some jumps, some discontinuities. And so if there's discontinuities in the derivative, that must mean that the original function must not be differentiable there. So is there anything here in these 4 functions that look like there's something that would be not differentiable? Give you a second. And if you notice, it would actually be graph number b, because graph b has these sharp turns. And so because there's those sharp turns, that means that it's not differentiable here. And if we're actually looking at the kinds of places in the graph, it actually does line up. This looks like about maybe -2 and +2 where we have the discontinuities. And if we go down to this graph, about -2 and +2. So b and 4 are matched together. So you can use a purple marker, star, or that's not 4, my bad. Star 4, and then star b. So we have these 2 eliminated. So let's start going through the other ones now. And the thing we're going to have to look through is that, remember, that the derivative represents the slope. So if we can look at the sign of the slope, then that's what it's going to be. So like if we had a negative slope, then the derivative would be negative, basically, because the slope is derivative represents slope. So that was kind of confusing the way I worded that, so I'm just going to show you it in an example through this. So if we look at graph A, it looks like the slope is negative all the way down into about -2. So because the slope is negative to about -2, that means the derivative we're looking for is probably going to be below the x-axis until -2. So we're just going to say that it's going to be negative from like -infinity or like the end of the graph, whatever, to -2. That's something we'll look for. And then if we notice that slope changes to positive, past 0 all the way into about 2. So we'll be positive from about -2 to about 2. And then we see that it curves and switches back to negative again. So it'll be negative again from 2 to like the end of the graph, whatever. Infinity, if you wanted to say that. So it looks like it's going to be changing negative to positive to negative. And the change points will be about -2 and 2. We're not giving numbers, but that's generally what it looks like. So if we look at this first graph, it starts negative, and then it's negative the whole time until 0, and then it's positive. So it changes negative to positive. We have 2 changes here, so it's not going to be graph number 1. And if we look at graph number 2 here, it looks like we got negative, and then until about -2. That looks like it's checking correctly so far. And then we have the whole graph to be positive until about x equals 2. That's checking. And then it's negative then on. That also checks. So it looks like number A is going to match with graph B. And that is actually correct, based off of the stuff we just found. So I'm going to mark with a blue star now. 2 matches with A. Moving on now. So I'm going to erase this stuff. But now let's move on to our next graph. We've done graph A and we've done graph B, so let's move on to graph C. Graph C looks like, so remember, on the functions, we're going to look at the slope, and then for the derivatives, we look at the sign. So let's look at the slope here. The slope of graph C looks like it's going to be negative, and it's negative all the way until we hit 0, and then it's positive. So let's check on our 2 remaining graphs, where it's negative until 0, and then positive thereafter. So let's just start from bottom up this time, since we were going top to bottom last time. Here it looks like we got, it starts positive, then it goes negative, then it's positive again, and then it's negative. We're just looking for one change from negative to positive, so this is absolutely not it. If we check this one, the graph number 1 up here, it looks like the whole thing is negative below the x-axis until we hit 0, and then the whole thing is positive. So it looks like 1 matches with C, and that is also correct. So here I'm going to match this with a green star. That green is so much lighter than the marker, but sure. And then, of course, by process of elimination, we can immediately say that 3 and D match, but we could also go over that the same way we did before. So D, it looks like it's increasing, so the slope is positive until about -2, and then it's negative until 0, positive until 2, and then negative until the end. Here, it's positive until 2, negative until 0, positive until 2, negative until infinity, whatever. So all the graphs check out matching that. And then there's also another way you could play into this. I don't fully remember it because I took Honors Math 3 a few years ago, but in Honors 3 you learned like degrees of graphs. So you know that if you have a 3rd degree graph like this, when you take the derivative, the 1 less degree is going to be 2nd degree, and that is going to be a parabola. So if you saw a graph like this, you knew you were looking for a parabola. So that is also another way you could play through all this. So there's just a few techniques you could use to match a function with its derivative, and I just showed you one of the main ones here today. Okay, so the end of lesson 2.3, we actually talked about a really, really big topic, which I'm going to show you now. So these are two functions that we've seen before, and we know easily how to differentiate. We can differentiate sine x. That's just cosine x. That's one of our formulas we learned in lesson 1. We can differentiate x squared. That's just 2x. That's power rule, another thing we learned in lesson 1. But what if we had something different? What if instead of sine x, we had sine of 3x? Or what if instead of x squared, what if it was x squared plus x, all squared? So what do we do in these cases? So to solve, take the derivative of these things, we're going to use something that I'm going to teach you called the chain rule. And so the chain rule lets us differentiate functions inside of functions. So I'm going to give a few examples. So we're going to first start by looking at that one equation I showed you, that x squared plus x all squared. So with the chain rule, what we're going to want to do is we're going to want to take first the derivative of what we call the outer function, and then the derivative of what we call the inner function. So in this case, the outer function would be this everything is squared. And then the inner function would be this x squared plus x. And so the way we identify this is there are like 4 kinds of things we take the derivatives of. We want to always see everything as these 4 derivatives rather than chain rule, and chain rule is just a kind of add-on that happens. So there are either going to be powers, products, quotients, or trig. So all the derivatives we take from now on, or until we get some more advanced stuff, we want to see it like these 4, and then chain rule just happens in the process. So the first thing we see, if we hide all this stuff in the middle, this is a power. So let's just do power rule on this while ignoring all this inner stuff. So what we have is the derivative of something squared. And the derivative of something squared is going to be 2 times that something to the power of 1. In our case, that something is x squared plus x. And so now that we've taken the derivative of that outer function, which was a power, we're going to take the derivative of that inner function, which, and before I had said, was that something, basically. So that function is this inner function right here, which is going to be x squared plus x. And so the derivative of x squared plus x is also using powers. So the derivative of x squared is going to be 2x, and the derivative of x is 1. So 2x plus 1. And so we have these 2 derivatives here, and rather than adding them together, what we're going to want to do is we're going to multiply them. And then that is how we take the derivative of x squared plus x all squared using the chain rule. We have another really similar example. So remember, look for power, product, quotient, or trig. In this case, we have some kind of power. So let's hide the inside function and just differentiate the power. So the derivative of something to the power of 4 is going to be 4 times that something to the power of 3. Inputting that something back into the original equation, we have 4 times the quantity x cubed plus 2x, all cubed. And then remember, we're going to have to multiply by the derivative of the inner function. And the inner function for us is x cubed plus 2x, which is another power. So we're going to multiply by this derivative. Derivative of x cubed is 3x squared. Derivative of 2x is just 2. And so that is our answer. Okay, so now generalizing this case of the chain rule that I've been showing you, we're going to have the derivative of f of x all to the power of n. So remember, if we have a power, what we're going to do now, from now on, what we want to see is hide the inside, and then take the derivative of the power. So derivative of something to the n is going to be n times that something to the power of n minus 1. That something for us is going to be f of x. And then remember, multiply by the derivative of the inner function. For us, we have the derivative of f of x. Deriving f of x, we are going to get f prime x. So this is the general format for this case of the chain rule I've been showing you. Take the derivative of f of x to the n. We get n f of x to the n minus 1, all multiplied by f prime x. But that's not the only way we could write the chain rule, and that's because if we take the derivative of sine of something, whatever, that's not a power. So chain rule has a more broader representation, and we're going to discover that through these next few examples. So let's say we wanted to take the derivative of sine 3x like we wanted to earlier. Now in this case, the outer function is trig. It's going to be sine of something. And then the inner function is just this 3x. So we do the kind of same thing as before. We're going to hide the inner function. So we're going to hide that 3x, and we just have the derivative of sine of something. The derivative of sine of something is going to be cosine of that something. This was a 3x. I accidentally slightly erased that. So derivative of sine of something is cosine of that something. In our case, that something is 3x. And then you have to take the derivative of that inner term, that inner function. Derivative of 3x is 3. And so simplifying this, or basically just rearranging terms, we're going to get 3 times cosine of 3x. So derivative of sine 3x is 3 cosine of 3x. How about something a little bit more difficult? So we're going to do this one now, which is derivative of tangent of x squared plus 1. Now, we're going to first identify what the outer and inner functions are. The outer function here is tangent of something, and the inner function is going to be x squared plus 1. So what we do is we hide the inner function, so the outer function is just derivative of tangent. Derivative of tangent of something is going to be secant squared of that something. Then we have to derive by the inner function. The inner function is x squared plus 1. Derivative of x squared plus 1 is going to be 2x. And so we just multiply those together. And so if we rearrange the terms, we get we get 2x times secant squared of x squared plus 1. And that is our answer. So now if we were going to generalize the whole most general term or general sense of the chain rule, it would be taking the derivative of f of g of x. And we're going to treat this that same way we did kind of with those trig functions. So if you we have to hide the inner term first. So the outer function is f of something, and then the inner function is g of x. So hide the inner term. Derivative of f of something is f prime of that something. And then now we take the derivative of this inner term. So inner term is g of x, so we multiply by derivative of g of x, which is g prime of x. So the most broad sense of the chain rule is derivative of f of g of x. We get f prime of g of x multiplied by g prime of x. Okay, so for the rest of the video, I'm just going to show you 6 more examples with the chain rule, and then that'll be about it. So this is our first example. Y equals 4 times the quantity 3 minus 10x, all to the 5th. And so first what we do is we identify. We're working with power, product, quotient, or trig. In this case, it's going to be power, so we're going to enact the chain rule. And like we did before, what we want to do is hide the inner function and just work with the outer function, which is this power. So derivative of 4 times something to the 5th is going to equal 4 times that something to the power of 4. No. My bad. I took that derivative wrong in my head. So derivative of 4 times something to the power of 5 is going to be 4 times 5 times that something to the power of 4. This is just pulling this 4 down and then doing basic power rule. The power, or deriving something to the power of 5, we get 5 times that something to the power of 4. So now what we do is we just pull this something down and write it in our derivative as that inner function. But now we have to actually derive this inner function. So derivative of 3 minus 10x, multiplying by that derivative, we are going to get just negative 10. Now if we want to simplify, we can. 4 times 5 is 20. 20 times negative 10 is negative 200. So we'll get negative 200 times 3 minus 10x, all to the power of 4. And that is our first answer. Okay, next problem. Y equals the square root of all this. So the square root of x squared minus 8x minus 20. So first identify power, product, quotient, or trig. This one's a power, and it's hard to see. But if we rewrite this, we're going to get x squared minus 8x minus 20. This is all to the power of 1/2. So that's how this one is a power. So now what we do is enact chain rule. We're going to hide this inner function basically, so ignore that. We're just going to derive something to the power of 1/2. Deriving something to the power of 1/2, we get 1/2 times that something to the power of negative 1/2. So if we write that something in here in that inner function now, and then next we just have to take the derivative of this, and this is just going to be power again. So multiply by this derivative, we'll get 2x minus 8. And there's not really much to simplifying we could do here. If anything, we just write 2x minus 8, and then we have r over 2. Bring this term into the denominator because it's a negative 1/2. We can rewrite this as a square root if we want to. So x squared minus 8x minus 20. If we wanted to, I now see that these all have a 2, so we could cancel that a bit. So we'll get x minus 4 over the square root of x squared minus 8x minus 20. Forgot the x over here, but yeah, that's our derivative. Okay, next one, we have y equals 9x over the cube root of 1 minus 3 to the x. And before we continue, I'm just going to rewrite this as 9x over 1 minus 3 to the x to the power of 1/3. So now we're going to look, is this a power, product, quotient, or trig? And the first thing that we see is that it's going to be a quotient in terms of the derivative. If the overall thing is a quotient, yes, I realize this is a power, but the overall thing is a quotient. So that's what we're first working with. So we're going to use the quotient rule to take the derivative. So quotient rule says we start by deriving the top. Derivative of 9x is going to be 9. And then you multiply by the bottom. So which is going to be 1 minus 3x to the power of 1/3. Then you subtract derivative of the bottom. And then now if we notice, derivative of the bottom is a chain rule. So using the chain rule on this, we identify first for this power, product, quotient, or trig again. This one's a power, so we hide the inside. Derivative of something to the 1/3 is going to be 1/3 times that something to the negative 2/3. So we rewrite what that something is in here. And then we take the derivative of this something, and the derivative of that is going to be -3. And then remember, we just differentiated the bottom. We're still doing quotient rule, so we have to multiply by that top. So multiply by 9x. And it's all going to be over the bottom squared. So it'll be 1 minus 3x to the power of 2/3. And so we can go through simplifying this. It's going to be a bit of a pain, but I'll walk you through it anyways. So if we look at the things in common here, both terms in the front, well, first what I want to do is I want to cancel this 1/3 with this 3. And then also this negative, in that this was a -3, so let's get rid of that -2 and turn this negative to a positive. So if I actually erase those things first, those ugly terms, what we have now left is the things in common in the numerator. We could factor out a 1 minus 3x to the power of -2/3, and we could factor out a 9. So let's do that now. We're going to have 9 times 1 minus 3x to the power of -2/3. And what's left here in the front, we got rid of that 9. And so -2/3 times what is 1/3? It's times 1. So we're just going to have this term to the first power. So it'll be 1 minus 3x. Over on this side, we factored out this thing, but we left the x. So we're just going to add an x. And remember, this is all over 1 minus 3x to the power of 2/3. We could do now is 3x plus x. That is going to be 2x. We have 3x plus x is -2x. My bad. Yeah. So we have 1 minus 2x on that term for the numerator. And we'll have this 9 still. But this 1 minus 3x to the -2/3, we can bring that to the bottom. And so because this term have the same base, we can add their powers. So 2/3 plus 2/3 is 4/3. So that will be 1 over, it will all be over 1 minus 3x to the power of 4/3. It's a bit much to try and word all of this with expanding or simplifying the quotient rule, I should say. But basically the main important thing was getting to this point before we simplified. I just struggled to actually explain how we simplified, but that's the main part of it. We did the quotient rule with chain rule at the same time. Okay, now, so for a break after that whole quotient rule thing, we got something a bit simpler. So now we identify power, product, quotient, or trig. This one is trig. So if we hide the inside, it's derivative of secant of something. Derivative of secant something is going to be secant of that something multiplied by tangent of that something. And then now we differentiate the inner function. In this case, the inner function was x cubed. So derivative of x cubed is going to be 3x squared. So if you want, you can just rearrange these terms. So we get 3x squared secant of x cubed times tangent of x cubed. And that is all that one is. Okay, we got another one that's also a bit spicy. So this one is y equals sine of 3x times cosine of 3x. And so before we actually differentiate, we got to identify power, product, quotient, or trig. And this is actually our first product. So we're going to do product rule on this. And another thing is, notice that both of these are functions inside of functions. So this is going to be this is going to be product and chain rule at the same time. So derivative of the first, this is the first term, this is the second term. So derivative of the first is derivative of sine of 3x. So what we do is we hide the inner function. Derivative of sine of something is cosine of that something. So cosine of 3x times the derivative of the inner function. Inner function is 3x. Derivative of 3x is 3. And then don't forget we're doing power rules, so don't forget to multiply by this second function, second term, or whatever it is. Whatever the word is, you know what I mean here. And then now we add, because product rule, we're going to derive this second function. So the second function is cosine of 3x. So this is chain rule again, so hide the inner function. Derivative of cosine of something is going to be negative sine of that something. And then we're going to multiply by the derivative of the inner function. Inner function here is 3x. Derivative of 3x is going to be just 3. And then remember, it's still product rule, so don't forget to multiply by just the first function on its own, which is sine of 3x. This part does confuse a lot of people because notice we have cosine 3x here twice, but just remember, follow the formula of chain rule and product rule, even if it looks a bit weird, and it will just work out fine. So here what we could do is rearrange some terms a bit. So this will be 3, and then cosine of 3x twice, so this will be cosine of 3x all squared. And then it could be plus, but actually no, we have a minus here for the minus sine x, so it'll be all minus 3, because this 3, and then sine 3x times sine 3x is going to be sine 3x squared. And yeah, that's about it. If you noticed, if you really like trigonometry, you notice this is basically in the format to do 3 times cosine of 6x, but that's a bit more than what we need to do in calculus. That's just if you really like trigonometry and you notice stuff. But this is basically our final answer. 3 times cosine of 3x all squared minus 3 times sine of 3x all squared. Okay, we're finishing off the video with pretty much a monster derivative for what we know so far. So this derivative is the derivative of cosine to the 4th of tangent of x squared. So before we actually derive, the first thing I want you to do is whenever you see cosine to the power of something, I want you to write cosine of something all to that power. It means the same exact thing, but it's a lot easier to see that this is cosine of something raised to a power. So once we've done this, we're going to identify first power, product, quotient, or trig, and the outer function is going to be a power. So we're going to do chain rule. So hide all the inner stuff. Derivative of something to the power of 4 is going to be 4 times that something. So 4 times cosine of tangent of x squared. And this is going to be all to the power of 3. Now we derive now we take the derivative of the inner function. Yes, that's what I'm trying to say. But if we notice, our inner function is cosine of tangent of x squared. And cosine of tangent of x squared, that is functions in functions again. So we're going to enact the chain rule again. So here our outer function is going to be cosine of something, and the inner function is going to be tangent of x squared. So deriving cosine of something, we get negative sine of that something. So in our case, it would be negative sine of tangent of x squared. Trying to count the parentheses here. Okay, and then so now we have to multiply by the inner function of this term. But if we notice, the inner function is going to be tangent of x squared. And that is chain rule again. So outer function here is tangent of something. Inner function is x squared. So derive tangent of something, you get secant squared of that something. And then you derive by the inner function. In this case, the inner function is x squared. Derivative of x squared is 2x. And then with that, we are finally finished doing chain rule. All we really have to do now is just simplify. So we have a negative, we have a 4, and we have a 2 and an x. So that will be negative 8x. And then we could really arrange these in any order we want. So I'll just write by times secant x squared times sine of tangent of x squared times cosine of tangent of x squared all cubed. There's really no formal order you have to do, but a really common way is do the least amount of functions in one and then increase to greater. So this is just negative 8x. This is secant of x squared, so that's one function in function. Sine of tangent of x squared, that's two functions in functions. Cosine of tangent of x squared all cubed, that's more functions in functions. So kind of do least to greatest, and that's kind of normal. And yeah, that's about it for that last problem. Yeah. Oh, hey. Now, before we close, I do want to discuss one thing, being that you might think, oh, when we have just a normal derivative, like of x cubed, why don't we multiply by the derivative of the inner function then? Like, do the same thing we did. We hide the outer function, and then we differentiate, so 3 times something squared. The inner something is x, so why don't we multiply by the derivative then? But we actually do. If you look, derivative of x is going to be a 1. And so this is just the same thing as we always do. That's going to equal 3x squared. So we actually always are enacting the chain rule. We just don't discuss it immediately when we learn calculus and derivatives and stuff, because it's kind of hidden at first, because derivative of x is 1, whatever, so it's not noticeable until we start doing actual full-on functions and stuff. But in that being said, that is about it for 2.3. And the only video I've yet to produce, because I'm producing all these out of order, is lesson 2.2. And I'll hopefully get that out to you soon. So yeah, good luck in calculus.